In this video, I'll be exploring EIP 2537, which adds a bunch of new precompiles to the EVM that allow for efficient computation along the BLS 12381 curve. If this sounds complicated, don't worry. I'll be breaking it down to its essentials. I'll be covering what precompiles are, what elliptic curves are, and why we need to handle them on the EVM level in order to enable some advanced cryptographic features. I'll be dividing this video into two parts, where in the first part I'll be covering what precompiles are and what elliptic curve cryptography is on a high level, but without going into any of the deep maths involved there. Then once you understand both of these, we'll be looking at some cryptographic schemes that are unlocked through the new precompiles that support efficient computations on this BLS 12381 curve, and also some use cases that enables. In the second part, we'll then be looking at what this EIP looks like at the Ethereum client level by looking at all the code changes that came along with it. Like I have done with previous EIPs, I'll be looking at the Revm code base, which is a Rust implementation of the EVM. And specifically, we'll be looking at the pull request that added EIP 2537 to that code base. This will not only show you how these new precompiles are added and implemented, but also how precompiles more generally fit in at the EVM level. All right, so let's get started. So looking at the spec of EIP 2537 itself, in the title it says precompile for BLS 12381 curve operations. So first things first, what are precompiles? So a precompile is like a built-in shortcut for executing very complex operations at the EVM level. Like a smart contract, they are linked to a certain address, but unlike smart contracts, these precompiles don't have any EVM bytecode stored in their storage. Instead, the implementation is hard-coded on the client software and therefore benefits from native performance and execution speed. That is obviously in stark contrast to normal smart contract bytecode execution, which goes through the EVM interpreter and gets executed opcode by opcode. And hence, they also have a fixed gas cost associated with them instead of what you would be charged if you implemented the same logic on the smart contract level, where you would be charged for each opcode that your implementation consumes. Now, there are a bunch of precompiles that already exists in the EVM, and one that you are probably familiar with is this EC recover method in Solidity, which recovers an Ethereum address that signed a given hash. Now, under the hood, this EC recover gets compiled to a call to address 0x01, where the code implementation of the ECDSA public key recovery on the SECP 256K1 elliptic curve is natively implemented. All right, so with this in mind, let's get back to EIP 2537. Which, as we said, adds a number of precompiles that handle operations against this BLS 12381 elliptic curve. But let's take a second to first understand what elliptic curves are and why we need to do math on them in order to enable some cryptographic schemes like BLS signature verifications, for example. So if you've heard about elliptic curves before, you already know that Ethereum uses this elliptic curve digital signature algorithm on the SECP 256K1 curve in order to authenticate transactions and making sure that they originate from the rightful wallet owner. Now, technically, all elliptic curves are represented by a shape that looks something like this here. And the curve itself is just a plotting of points along the x and y axis that make this specific equation true. So if I pick this point, for example, and plug in the x and the y value into this equation, this will resolve to true. And every elliptic curve basically has a different a and b coefficient that affects the shape of this curve slightly. But obviously not only the shape, but most importantly, like security and performance aspects, as well as certain math operations that you can actually do against this curve that are useful for various cryptographic schemes. So for example, this new BLS 12381 elliptic curve that is now being supported by the EVM through this EIP 2537 supports what is called pairing operations on the curve, which you don't really need to understand in detail, nor do I, by the way. But basically it allows a bunch of powerful cryptographic techniques like aggregating signatures and some zero-knowledge proof stuff. Now, cryptographic schemes like ECDSA we had a look at before, or BLS signatures, for example, do math against this curve by, like, for example, adding 2 points. And actually, if we look at the spec of EIP 2537, we can see that one of the precompiles being added is a addition operation on this new BLS 12381 curve. So in any case, any kind of cryptographic scheme that uses elliptic curve to do math falls under the category of elliptic curve cryptography. And all they really have in common is that they rely on mathematical problems that are easy to compute one way, but which are extremely hard to reverse without a special piece of information, like a private key, for example. And by hard to reverse in this context here, I mean that they computationally infeasible without the knowledge of that specific private key. How they managed to do that is out of scope of this video, but I have added a good primer in the description notes, and if you're interested, you should definitely check it out. Now, with all that high-level overview, let's have a look at why we want to be able to support this specific BLS 12381 curve on the EVM level. And a major reason for that is that it supports this so-called BLS signature scheme, which is already used by the Ethereum consensus layer, as in when validators sign off of something, they use that scheme to sign that they agree, basically. And BLS signatures can be aggregated into one, which is enabled by this pairing operation on the curve that we talked about earlier. And that makes it very efficient to validate the correctness of something that many different entities have signed off on. Now, how can that be used in smart contracts, for example? Well, in some cases, it might be quite useful to be able to verify finality, for example, by checking that enough validators have signed off on a certain epoch, especially for applications that are sensitive to reorgs, for instance. And this aggregation of BLS signatures, for example, could also be used in multisigs, where many entities could sign something and then those signatures get aggregated into one, and that can be very efficiently then verified on the smart contract level to check if a certain quorum has been reached. Another area where this BLS 12381 support on the EVM level is very useful is within the zero-knowledge cryptography space. All these proof systems and privacy protocols and so on can make use of those precompiles. And again, that curve is useful for zero-knowledge cryptography because of these pairing operations that are possible that we talked already about. Obviously, there are some more use cases that are enabled through these new precompiles. But there's no point in listing all of them here. All we really need to understand is that this EIP increases the EVM capabilities to support some of the more advanced elliptic curve cryptography that is out there. But with all that in mind, now that we understand the EIP on a high level, we will now be going to part 2, where I'll be looking at the actual implementation of that EIP on the Ethereum client software level.